Well, my name is Jim Wilson, and I'm the co-author of an upcoming book entitled Windows CE Systems Integration, or System Integration. And that's really a book, it's kind of a soup to nuts sort of book that helps you if you're integrating CE on a custom platform, gives you some idea of where to start, what sort of things you have to do. Even goes down to the point of letting you schedule the project, giving you some idea of what the overall project dimensions are. I was going to get to that at the very end, but hopefully at the end of the year, hopefully. I say hopefully because we're trying to track some of the releases that Microsoft's coming up with, the 2.1.2 and 3.0 release. It's a bit hard to do that, but that's our target.
What year?
This year. I hope. Again, just a brief biography. I've been a software engineer for quite a while, and I've integrated CE on a few platforms, and I've gone through the process that you're probably going to go through in your own custom hardware as you begin to make CE functional. And I've done a few publications, a few magazine articles on device driver development, and as I mentioned, we've got this book coming. And I've also developed device drivers for Windows CE desktop, so hopefully I can bring a unique perspective, both the desktop side of the device driver world, if you're coming from that world, trying to develop device drivers for CE, and also the embedded system side, which I have a lot of experience in as well. So today we're going to cover we're going to start off with just kind of covering some concepts that are necessary, I think, to understand Windows CE device drivers as a whole. We're going to talk about types, classes, and models. We'll go over the device driver architecture, and I'll throw a lot of terms at you at that point, which you may not totally understand in the beginning, but kind of keep that diagram in mind and refer back to it in your handout. As we progress, it'll make more sense. Also, by the way, with regard to the handout, the one you have will be a little bit different than the one I go over. I change the order of a slide, and then I change the content of one, and I'll try and bring it up when it happens, but it won't be too hard for you to figure out where we're at. We'll cover the standard device driver models that are offered by CE, and then we'll cover some basic development practices. There's some things that you always have to do when you're writing a device driver. Of course, accessing the hardware is one of them. And then we'll cover the installation process, not of the kind of driver that you would have on a custom platform, but the type of driver you might write if you wanted to support a PC card or a USB type of device for a standard CE platform, such as an HPC or a palm-sized PC. Okay, device types. These are a couple of terms I use and have been used in the past, but I want to, by Microsoft in older documentation, but I want to clarify how I'm using them, but I think it's valuable. An onboard device is kind of what you'd expect. It's one that's stuck onto the board, it's soldered to the board, it's a part of your custom platform, it's not accessible by the end user, it's something that you expect to support when the CE kernel is first booted. An installable device is, like I was saying, it could be a PC card, it could be a USB device, it's something that the user might routinely insert and remove from the device, and driver requirements for each of these can vary. So what's a driver model? You've probably heard it referred to a lot, and I think it's important to define it in this context. And it's really a mechanism. It doesn't necessarily dictate an API, though it can. And the mechanism allows us to define, oftentimes, layers in the driver. Windows CE supports different driver models used in different situations, and it also, in part, supports some of the 9xNT driver model. And you'll see what those are as we go forward. And interestingly enough, as you learn more about the driver architecture, you can kind of see how Microsoft has extended their existing driver architecture to support new driver models. And you'll see how an old driver model can be used as a mechanism for doing that. Now, some of today's driver models for Windows CE are the stream interface model. We'll be discussing that in this presentation. The native driver model, we'll go over that a bit. We won't really talk too much about NDIS 4.0. It's supported for the most part with some differences. Printer mini port is also supported from the desktop model again, but with some differences. Windows NT ACM, the audio control manager drivers, is supported in part, mostly with some tools to make the porting task easier. And then USB drivers, which is a unique model for Windows CE. Hey, what's a device class? Well, device class, kind of as the name implies, is just a way for you to group common attributes of a given device so that we can define that device in terms of those common attributes. This allows us to support those common attributes with code, so less code needs to be written by you for the hardware-specific aspects, those proprietary extensions. Now, Microsoft defines device classes, and you'll see why that's important later. And some of those device classes we'll be going over just as a big list. The primary calling module, it's important to remember for drivers that support a given device class, is GWES, which is the graphical windowing and event subsystem you've probably heard about in some other presentations. That's not provided in source form, and that's one of the reasons why Microsoft is the one that does all the device class definition, because they define what APIs go between you and that operating system module. And without access to their source, you really can't change that. Device classes is a big list. It's only a partial list, and I suspect as time goes on, it's just going to keep growing. But these are some of the devices that out of the box, Windows CE gets you started with some sample code, shows you the way to go. And one interesting one to note is that the serial driver, as we'll learn, is actually considered a native driver, but it borrows from some of the stream interface mechanisms to implement its upper layer, which we'll talk about in a moment. Okay, I'm going to try some animation here with these slides. I'm new to slide animation. I can't tell you how much time I wasted on this. Here we go. All right, the device manager is the thing you'll probably, oh, thank you. Yeah. Yeah. That's about an hour of work right there. The device manager is the thing you'll probably get to know the most. This is the thing that's responsible for controlling and stream interface drivers. And the upper layer of a stream interface driver is the stream interface, and the blue box, which you'll see in the other modules, is the name of the driver model. The lower box is the hardware interface, the kinds of functions you might use to gain access to your device. Now, in this particular stream interface driver, I'm assuming you support a PC card, so I'm assuming you're going to use card services to access that hardware. I think that's it for that one. Another type of driver model, as we mentioned, is the native driver, and we'll talk about those two layers up above the blue box and below it. And this is an example where the native driver in its upper interface can actually borrow from the stream interface model in the implementation of that upper interface. Oh, there was one more. Now you can see this is interesting. The Endus driver, the wrapper itself, is implemented as a stream interface driver, but the Endus mini port, to be compliant or to be as close as possible to Endus 4.0, is its own driver model. But the Endus wrapper itself is another type of driver using Device Manager, and it also pulls in card services because in typical cases you're supporting a PC card acting as a network interface. And again, another thing, back, there we go. Another type of stream interface driver that's often used, or that's used to implement USB drivers, is a USB driver. USB-D is the module that we'll talk about a little bit. And then the USB driver, again, you can see that the stream interface, the USB-D, we can call, I've kind of coined a term called the driver control program. You can think of the Endus module and the USB-D module as these driver control programs. And again, they use a stream interface, but yet the USB driver is its own model. Now, GWES is the other primary module that's going to manage drivers for you. And there's different types of native drivers, and we'll talk about those. They have an upper interface called DDI. We'll get into that. And again, you see native driver again, except this type of native driver has a DDI interface, which is implemented specifically for that device class. It's not implemented using stream interface, which we'll talk about. So it's going to get a little confusing until we hammer out some of the details. Again, as I mentioned, that the device classes, another way of looking at device classes is the DDI interface associated with each device class. That's defined by Microsoft. And I'll tell you what DDI stands for in a second. So basically, the device driver architecture consists of a bunch of DLLs and a bunch of object module libraries, mostly DLLs. If it's an object module library, it's typically linked into another module or potentially to another DLL. And in that case, you're just changing a portion of the code, and the code you change is being linked into a binary. Now, the great thing about being DLLs is that it runs in user mode, which gives you access to a lot of the same facilities that application developers have had for a long time. So in theory, if you wanted to, you could use MFC, COM services, even ATL to develop your driver. There's nothing that requires you to do that, but now you can start to think in terms of being an object-oriented driver, and it's not something in the embedded world we've had the luxury of doing. The other advantage of this is that it adds stability since the kernel is protected from a driver. And it also gives us the ability, if you have a CPU that doesn't have a specialized interface like a JTAG port or a BDM connector, Windows CE will still provide debug capability for you in the context of the kernel. So the kernel is loaded first and the drivers are in user mode. The kernel can actually control the execution of the code. That wouldn't be possible if the drivers coexisted with the kernel. Let's talk about the device manager a little bit more detail. Again, as I mentioned, it's loading and unloading the driver. It's translating application level calls, and you'll see that there's a close correlation between the required entry points for a stream interface driver, which device manager supports, and the actual application level calls. It's also responsible for sending power management notifications into those drivers, and also for enumerating PC card devices and walking the registry, figuring out which driver to load. Another interesting point is that it exists in its own separate process space, and each one of these drivers that device manager is actually managing exist as DLLs in the same process space. So this has implications for buffer access, which we'll talk about in a minute with some example code. And it also has implications in the sense that a single driver instance, even though it's a DLL, has to support a lot of other applications which may attempt to access that driver. Only that one instance would need to support it. Even though it's a DLL, it's not linked, separate instances are not linked directly to the app. Now here's an example of some of the registry keys that device manager is responsible for. Built in is a registry key that allows you to have the driver loaded at the time the system is started without any kind of device enumeration. PCMCA, on the other hand, the keys underneath this key, the PCMCA key, are usually the plug-and-play IDs. And when device manager detects the insertion of a card, it'll try to match that plug-and-play ID in the registry with the one it detects in the card, and then load the associated driver. However, it's possible for you to write a driver that's not specific to a particular PC card, and then you put your driver under the detect key, and there's a special entry point in your driver that device manager will call, and in effect to ask your driver, can you support this card? If you reply with a true value, then your driver gets loaded. So you're not, in effect, what this gives you the ability to do is support a class of devices without being specific to one plug-and-play ID. Next thing device manager does is called register device. That's a function that's also available to applications if you want to manually load a driver. And what it does is it locks a driver in working RAM so it doesn't get demand paged out. That's important, especially if you're going to be servicing some interrupts. And it allows you, and it also creates a device file name for you. This function does. And the device file name is something that the applications will use to specify your driver when they attempt to open it. Another point to make too is that the active subkey, as device manager actually loads these drivers, it'll update another registry key to keep track of the ones it's already loaded. Now it's not recommended that you actually pull values from that key, but it's interesting to use to at least see, even for debugging purposes, that the driver's been loaded. And you may have a need in your application to identify an already loaded driver, especially if that driver only supports one instance of one application accessing it at a time. The stream interface driver model is used the most commonly. It's one you'll probably get the most familiar with because it's so flexible. It kind of consists of the standard Win32 file I/O interface, borrowed from the Unix world. It's very familiar. You've probably seen it in the Win32 calls like create file, read file, write file. Except it's a little bit different in this case. When we make a create file call, we refer to that device file name. It supports installable devices, as I mentioned. And it's only the APIs or the entry points into your driver are only exposed through device manager. That's kind of what you'd expect. But as we see, when we look at other driver models, there are other driver models that could potentially be accessed directly by the application. And as I mentioned before, it's often used in combination with a native driver. So the native driver may use the mechanism, the stream interface, to implement its upper edge interface. What's some of the required entry points? Listed kind of in an approximate order of how they're actually called. The initialization entry point is called at the time the driver is loaded. And that's kind of the place where you would initialize global information associated with your device. I/O control associates with device I/O control in the application. And that's the call that's made just as a generic way of extending the functionality beyond the limitations of these entry points. The open, read, write, and seek, those correspond to what you'd expect in the application with the open file or create file in this case. Open is used if a given application wants access to that driver, then this entry point in your driver gets called. So if you only support one instance and you happen to get called again and you're still already open, you have to return back an error. Power up is called and power down are called. Power down, you can't really do too much. In the implementation of power down, you're focused just on saving that information that power down did occur. You're not actually unloaded. Actually, you could be unloaded depending on the circumstances, but it's most important that you just keep track of the fact that the next time you run, that you want to know that you were previously powered down in case you need to reinitialize your hardware. And deinitialization is called when the driver is unloaded and closed. It's called when the file itself is closed from the application through a close file call. Native driver model supports onboard devices only. That means that in this a native driver, as we described onboard devices, if you're building a custom platform, you may have specific peripherals you want to support, and that's what the native driver model is typically for. It supports a class mini-port layering, which is great because that means the thing you're going to focus on is the platform-dependent piece of the code, which at the bottom of the slide we're describing as the PDD layer. The PDD layer contains all the code that's necessary to access the hardware, and that's really, as I mentioned, the focus of your changes. The MDD layer is provided by Microsoft, and that usually represents the collection of all the code that's common to that device class. And it's the one that has the interface with specific entry points that are required for communication with GWES. GWES will call down into it, you'll call back into GWES. And typically in a native driver, it handles the interrupts for you. The upper edge interface, which we talked about in that diagram, in the architecture diagram, for the MDD layers is DDI, which stands for Device Driver Interface. So it can get a little bit confusing. The layer itself is called MDD. The functions that are used to access that layer are called DDI functions, or the DDI interface. Those functions at this level, as I mentioned, are defined by Microsoft because GWES is the one that's calling it. You don't have any abilities to change GWES specifically. And PDD, the Device Driver Service Provider Interface, that's what DDSI stands for. And there is under certain circumstances, it is possible, since the MDD and the PDD layer are both provided in source form, it's conceivable that the interface between those two layers you could eliminate. If for some performance constraint you don't want that extra interface or the extra overhead of calling between the two, you could rewrite PDD and MDD. Of course, you still have to, at the DDI level, still have to export the same functions, but you've in effect created a monolithic driver that perhaps meets your performance requirements better. In the USB device driver model, there's two primary modules that you'll see provided in source form. HCD is the one that's responsible for interfacing to the controller, and it's used by USBD to identify an inserted device. USBD is the module that implements most of the high-level calls that applications would access for pipe management, for data transfer, for framing. These are things that a USB or a universal serial bus device would be concerned about. And the HCD, finally, it provides device enumeration, as I mentioned, and that's important for USBD because, as we'll see, somehow the drivers associated with that USB device need to be loaded. Now, if in an interesting case for the USB device driver model is that what happens is as the device is enumerated, each USB driver is loaded, and it's asked, are you the one that I need to keep loaded for the specific device? If you say no, then you get unloaded. And it'll keep doing that until it finally locates a driver that's appropriate for that device. If, however, you are supporting a device that has additional endpoints, in other words, it's a compound device with 2 or 3 functions built into it, you need to load the other drivers associated with those additional functions. The other thing that's interesting about the USB driver model, it's different than the stream interface in the native driver model in that when you obtain data, either transmitted or received from your USB device, you call into the GWES module to expose that data, or it might potentially call into you. And an example of that you'll see in the sample mouse driver, where the primary interface for exposing your data with that sample mouse driver is through this mouse event function call. Now, you don't have many required entry points, which we'll see in a second. There's only 3. Unlike in the other driver models where you have a more defined list of required entry points. So if you're not supporting an existing device class in the implementation of your USB driver, well, let me say if you were. If you were supporting an existing device class, you'd have access to functions that GWES exports for the device classes it supports. But if you had a great whiz-bang USB device that hasn't been exposed before in the context of a standard device class, it's conceivable that you would expose APIs directly into your driver that applications could access. In effect, then, you're using the USB driver model just to get loaded and just for purposes of enumeration and for transmitting and receiving data. So in this case, an application we call load library, which if you're familiar with Win32 programming is pretty common, and get proc address. So that's just a way for an application to say, give me all the entry points for this DLL. And only 3 required entry points. Again, as I mentioned, they're just focused on loading the driver, not focused on actually exposing a particular set of services to an application. Device attach, install driver, and uninstall driver. Other device driver models that CE supplies: the Indus 4.0 mini port, the printer mini port, the audio compression manager, and many drivers that I mentioned, driver models you might find as you study the online documentation, you look at sample sources, you might feel like you're looking at a little bit of both, and we talked about that. And then you could, as we mentioned, you could implement your own driver model if you wanted to, much in the same manner that USB and the Indus driver model has been implemented. Now this slide's actually a little bit different than the one you've got. Processing interrupts varies by driver model, and the reason for that is that if you are trying to be conforming to a driver model, then you need to use the driver model's mechanism for gaining access to those interrupts. Indus has its own way of doing that, so does the PC card. Card services interfaces for gaining access to interrupts. But in general, all interrupts go through an ISR. It's implemented in the OAL, OAL being the OEM adaptation layer. And that ISR is written typically by the provider of the custom platform. If you're the person with the custom platform, that's something you're going to have to write. All that ISR is supposed to do is identify the IRQ itself and associate it with a logical ID that you would later expose through a header file to other code that needs it. So you don't do too much. If you do a lot, it's a well-known or somewhat of a problem with CE right now, is that if you do a lot in that ISR, you're going to cause a big interrupt latency to occur because all the interrupts are disabled at the time that ISR actually fires. So you want to get out of it very quickly. Now, once you get out of the ISR, as I mentioned, it's returning a logical ID. That's what activates what's called an interrupt service thread in your driver. And we'll see a specific example of that shortly. So at the time the interrupt service routine exits, all the interrupts are re-enabled. So that's good. You reduce the potential for interrupt latency, except one, the one associated with the actual interrupt that fired. It's up to the interrupt service thread to re-enable that interrupt. And ISTs, because they're very closely associated with interrupts, generally run at a much higher priority. And we'll see some specific code for setting up an IST as well. There's two priority levels that you can run. Typically, you'll see most sample code running at its thread priority highest, and then another one that's thread priority time critical. And time critical is higher, and that's the kind of priority you would use if you needed to run to completion, with guaranteeing that in your IST you wanted no preemption whatsoever. On the thread priority highest, you could be preempted by other ISTs that are running at that same priority level, or any other thread for that matter that's running at that priority level. That may be okay for you, may not be, so it's something to keep in mind. But of course, if you pick the time critical option, you again expose the system to more latency. Now, you probably can't read this, and unfortunately, you probably won't be able to read too much of it in the printed handout. But let me just go over the top-level parts of it. What I'm trying to do in this diagram is kind of show you the life of an interrupt, where it begins and where it finally ends. When an interrupt occurs, jumps into the CE kernel, and there's an exception handler there that does this disabling of all interrupts. It determines which ISR, it executes the ISR, and in the interrupt service routine, as I mentioned, we're associated with right here with the logical interrupt ID, which ultimately gets handed up to the IST that's appropriate for that logical interrupt ID. So if you've registered your IST, and there's a function for this we'll see, you're the one that'll get activated if you registered yourself for that logical interrupt ID. That's the mouse, there it is. We're back here in the interrupt service thread. And the interrupt service thread does all the work. You know, you're getting your data, you might be accessing some of the data and writing it into a pointer that the application has supplied. And when you're finished, you call interrupt done, which is down here, and you can probably barely read that. And one other thing I needed to mention, if I haven't already, the final version of this handout, which is more readable, will be available on the website. And then once you call interrupt done, then you OEM interrupt done, which if you're implementing an OAL, you're responsible for implementing, gets executed and passed from user mode where your driver is running down into kernel mode where OEM interrupt done exists. And at that point, the interrupt itself for that specific IRQ line is re-enabled. And now everything's back on. Okay, so here's some actual code. This is a pretty typical example of an interrupt service thread. So at this point, you can assume that this thread's already been created with the create thread call. The first thing you're going to do in the thread is set your priority. And here, I chose to set it as priority highest. The next thing is you're going to create that event. The event is very important because that's the way that the interrupt service thread gets signaled by the kernel that it's time to start processing the interrupt. Get the mouse cursor back again. There it is. And interrupt initialize is the function call you're going to make to tell the kernel sys_intr my device underscore function 1. That's the logical ID, not the physical interrupt line, but the logical ID that the custom platform vendor has decided to associate with a physical ID. And there's really no requirement. This could be a logical ID associated with one physical interrupt line, and maybe there's more intelligence in their ISR to determine which type of logical ID they want to associate with one physical interrupt. And down here, you're in an endless loop. You're waiting for something to happen, and you call the wait for signal object. That puts you to sleep. And you're asleep using the event handle, which was created back up over here. And until that event handle becomes signaled by the kernel, you're not going to do anything. When you do wake up, where the ellipsis is, those 3 dots, that's where you're going to do most of your work. At the end, interrupt done is going to be called, and then that goes back into the kernel, as we mentioned, and causes an OEM interrupt done function to be called. Okay, so accessing physical resources. That's another thing that most drivers, virtually all drivers, are going to have to do. Now, as you remember, we said that the drivers were implemented as user mode processes. So that means you can't just access your baseboard address or your frame buffer directly. You've got to do something to tell the kernel that that's a space that you want to access without causing an exception. And there are functions such as mmmap.io space, which you might remember again from the desktop side. It's borrowed from desktop side, works the same way. And that's implemented in this library called CEDevCon. And that makes it pretty easy. It's one function call. It says, here, give me access to this region of memory. And it tells it that I want it uncached access, so you don't have any problems with getting data directly from the hardware. So that's just one step you need to take, something to keep in mind. Now, other driver models like Endus don't require you to call the mmmap.io space function. They have their own functions for doing that. And if you're familiar with writing Endus drivers, you'll know what those functions are. Okay, some more example stores. Now, it's interesting, at the very top line, you'll notice that we've got uncached offset. And you've got to know what your particular CPU typically maps its uncached memory space to. This is most commonly the value, but you'll need to know that specific for your platform that you're supporting. And I've created a macro here that does nothing more than just set the high bit of that address. So it's important to keep in mind you just can't use, when you're calling this function here, mmmap.io space, you just can't call it with these constants. You need to set the high bit. This gives you access to the uncached memory, and you get a return value here, which is saved in a variable p mapped memory. And that's the variable that you'd use from that point on to access those addresses, access that physical device. The value of it you don't care about because it's probably not going to correspond to your base address. But you just know that it will ultimately result in access to that hardware. And then when you're finished, there it is, mmunmap.io space will get called, or you would need to call that, I'm sorry, and that will deallocate your physical access to the memory. That's an important thing to do, especially if this parameter is being passed around. You want to make sure that the access to that physical memory is controlled. Another thing you're probably going to want to do at some point is pass pointers to drivers. Now, if you're writing a stream interface driver, device I/O control is something that an application can call, and it's a pretty generic function. It basically takes an input parameter, an output parameter, and a couple of length parameters. It's pretty basic, but it's flexible enough to extend the required entry points for a stream interface driver. Now, if you happen to be passing a pointer to a structure that contains other pointers, device I/O control isn't going to help you there, in that it only knows about the pointer that you passed in the parameter list. It doesn't know what the pointer points to. If it's other pointers, you got to do something about that. And the reason is that because the driver's running in a different process space, C is a protected protected operating system. It won't allow you to access the pointer that the application's passed to you. So what you do to get around this is use this function called map pointer to process. The first parameter is the address that needs to be mapped, and the second parameter is the ID of the owning process slot. Now what that means is that this could be the ID, what it means is that this is the ID of the process that actually owns that pointer, where it exists. Now there's two ways you can get this information. You could call it with you could obtain it with get current process or get caller process. And get current process is the one that the caller would use if the caller wanted to help you out and provide you with this special mapped pointer. So if you were the caller, in this case an application, you'd have to call this function map pointer to process repeatedly for each structure member which might contain a pointer reference. Or you could, as the driver, take care of it for the application, and in this situation you'd call get caller process from within your driver. Okay, well, let's say you want to support asynchronous I/O with your driver, which means that, let's say in this particular case, you have an IST, interrupt service thread, and the application previously passed you a pointer, and you want to use that pointer to write data into that. And then maybe there's some event mechanism you're using to signal the application to say, hey, I've got data for you, and it's in your buffer that you gave me before. This way it reduces buffer copies. Well, in that situation, since the IST is in a separate thread, the way this context switching works within CE, when that thread is active, the process slot for the driver is the one that's active, which is the process slot for device.exe. The process slot for the pointer that was passed to you by the calling application is not. Now you can't use map pointer to process because map pointer to process is limited to just giving you access to the currently active process slot. But there is a way around this. The function called setProc permissions will do the job for you. And if you look at this code, the very top line, get current permissions, is basically a function that says, okay, I'm in the driver's thread, and this is the first step that I'm going to take in gaining access to to my application's buffer pointer. But I need to know what my current permissions are because I want to restore them back later. This is a pretty powerful function, and if you want to make sure that you put your permissions back to the way they were, or you eliminate all the benefit of this process protection. Okay, and then in the next function call, you say set proc permissions, and the parameter that we're passing was a global variable that's already been initialized some other place in the code, probably in that first function that the driver itself used to say, here's my buffer pointer for asynchronous I/O. At that point, while you're still being called, while you're still in the process slot of the caller, you would get current permissions and save it while you still can. So at this point, I'm using that save value, and I'm saying, give me the same permissions that the calling application had when it first set up this asynchronous I/O. Well, then we're in good shape, because now I've got all the permissions that I need to access the buffer pointer, which corresponds to a different process slot, which is not currently active. And then at the very end, when I'm finished dereferencing the pointer, I set the proc permissions back to what they were, like a good driver citizen. Okay, so what do we do with device driver installation? It's less of an issue if you're writing, as I mentioned, a custom platform, because you'll include the drivers in the definition of the default registry. That means that the drivers, when the platform boots, will just automatically load because they're part of your ROM image. But what if you're a person that's developing drivers for a PC card, or a driver that's actually bundled with a PC card that gets sold to CE users? Well, in that situation, you've got a few problems you need to solve, and that you've got different binaries that you have to build for all these different processors that are out there for various CE devices. And with the latest release of CE services, the application manager was introduced, which gives you the ability to create an INF file. And the INF file is what's kind of used as a script in effect. Well, it's more like a description, not really a script. It's used by the cab wizard, which then constructs a cab file, and that cab file will have all these different binaries, and it'll keep track of which binary is associated with which target CPU. It also keeps track of the registry entries required for the installation of your driver and the destination directory, of course. Well, that'll take care of you in one way. There's another way you can get your driver installed as well. If you knew that the driver was already on the target platform, maybe because the user just through CE services just dragged and dropped it into their file system in the object store, then when the device gets inserted, Device Manager will then say, it'll look through the registry, it won't find any drivers that correspond to that dynamically enumerated device, and it'll pop up with a little prompt or dialog box for the end user. At that point, the end user has a chance to type in the name of the driver. Now, if the name of that driver is your driver, and if you have one of these functions, the function being called install_driver, you then have an opportunity to write all the registry entries that are needed so you can get automatically installed. You write all your registry entries, you do whatever you need to for setup, and then you return. And then Device Manager will re-enumerate the device again. It'll search the registry in hopes that it can then find the associated driver. So we went through that pretty fast. So we have plenty of time for questions at the end. In conclusion, I think hopefully you see that the CE device driver architecture really is very flexible, which means it'll support a large number of devices in the future and probably be extended in different ways that are dictated by all these, the device requirements that come up from as yet uncreated devices. And there's a lot of support for existing device classes. It really makes it nice because if you've got a custom platform and you want to do this, the basic keyboard, the basic mouse, maybe a touch panel, you can kind of pick and choose, and CE lets you get a head start in developing these drivers because they're already supported, already provided in the platform builder. And as we mentioned, the interrupt processing is different for each driver model. So it's not possible for me to tell you today, here's one driver model that'll solve all your needs and here's how it's done. You've got to look, you've got to take your device and then try to match it to an existing driver and find out what model that existing driver is using, if it's there. If it's not there, then you'd consider the stream interface model as your default. And again, as we mentioned, access to physical resources, that requires a little extra care. If you're used to embedded systems development without enabling the protected mode features of your CPU, that's going to be a new thing for you. And the driver installation, of course, is real important. And that's something that, again, you don't have to worry so much about with a custom platform when your drivers are part of the ROM image, but it's real important if you're bundling with a card of some kind. And don't forget, when the Windows CE System Integration book comes out, support your struggling authors. It's Aspi Habewala and myself. So at this point, let me go ahead and open up the floor to some questions. There's a microphone over here. Or if you scream, I'll go ahead and repeat the question. It should, the system is smart enough to reject the call. There'll be a return code that indicates that it didn't succeed. Oh, I'm sorry. I forgot. The question was if you're calling mmmap IO space, and that space has already been allocated, in other words, the mapping of the virtual memory to the physical memory has already been done by somebody else, by some other driver, what happens when you attempt it? Now, as far as I'm fairly certain that when you make that call, you'll get back a return code that indicates that physical address has already been allocated. I don't believe you can share it, but I'm not sure. Does anybody here have any knowledge otherwise? Okay, go ahead. I'm sorry, can you say it again? Okay, very good. Can you turn that one on? Yeah, the comment that was made is that mmmap IO space is actually implemented and provided in source form using a lot of other functions, such as the ones you mentioned. There's a virtual copy and then one other one. And the comment was that if you use those functions, rather than using mmmap IO space, you can share access to a single physical address space. Did you want to say something?
mmmap IO does do that.
It does do that? Okay, thanks.
More than
Why don't you stay up here just in case any other ones come? Any more questions? At the microphone?
Yeah, I had a question in regards to register device and using multiple instances as you start plugging in more and more devices that'll call that driver. So register device takes a prefix and an index value.
Yes.
And in my particular case, I could have several pieces of hardware that plug in, and I export a stream interface, and so I need to call register device. And in my particular situation, my prefix is also used by other drivers outside of my control. So, of course, I need to use a individual index value. So I want to know what the best way of finding a unique index value would be. I know that you mentioned you could walk through the active registry key, and I could look for the prefix values and just find the lowest one. But as you mentioned, and also as the documentation mentions, pulling active device or the active key is not really recommended. I was wondering if you had an alternative or...
Well, I thought there was I don't remember specifically what it was, but I thought there was a registry key that lets you say that the device ID will be allocated. It's not a specific device ID, but it will just pick the next available one. Is it? Go ahead, I'm sorry. Did everybody hear the question, by the way? Let me repeat it, because it's kind of a long question. The question was, and correct me if I'm wrong, so if I get it wrong, you've got a situation where you know that your device prefix, your three-character series, is used by other device drivers, but you know that you need a device ID, and you're not sure which one you're going to get because the other device drivers are allocating them and using them at the same time. Did you need a specific number for your device index?
I don't need one. I just need the next available one.
Okay. There's actually two APIs. There's Activate Device and Register Device. Activate Device takes a pointer to a registry key hive, like the built-in device settings, the same type of structure. And if the device index is not specified there, it'll find the first one. Underneath it, Activate Device calls Register Device. And all it really does is it starts at index 1, and if it gets an error from Register Device, that's typically the return code from getLastError, you can determine that it's not a unique name. You can just call trying for device 1, device 2, and then we start at 1, loop to 9, and then loop around back to zeros, because you can have 10 for an individual prefix. And if you want to, you could then use multiple prefixes.
Is there a way that I could exclude the first one and actually start on the second one? Because I know that, in fact, the built-in driver uses 1.
Well, calling register device yourself, you could start with 7. You could start with whatever number you want.
If he doesn't control the application.
If you're calling activate device, then you can't. It will do it automatically. It'll look in the registry if there's an index value in there.
Yeah.
If there's not, then it'll just start at it'll start at 1 and find the first available one.
Okay. Actually, I did see activate device in some sample code, but it is not in the documentation.
Yeah, that's new for
device is it.
That's new for 2.1.1.
Thanks.
Question of on ISR and ISTs. ISRs basically defer the process to IST routines. Is there any way I can assign priorities for time-critical ISRs?
Priority.
Yeah.
That's something you would generally do wouldn't the CPU be the one that's responsible for setting the interrupt priority?
Well, I have a situation, say CPU contains, say, one IRQ. Then I go in, look at the different interrupt controller, what is the cost for different, different interrupts. Now within there, I may have to process, there's no priority. Hardware priority is their CE. Does allow me to process put the thread in the top priority or anything like that?
Once the ISR is running, then all interrupts are off until the next major release, the CEDar release, which does support nested interrupts, in which case, if a higher priority interrupt does occur, it'll interrupt a lower priority ISR that's running. But in 2.1.1 and 2.1.2, which will be available shortly, we do not support nested interrupts. So once an ISR is running, it will stop other ISRs from running.
Is this support is going to be there in 2.1.2 also?
The nested interrupt support will be in 3.0. And there's a talk on the real-time OS that's coming up on Tuesday afternoon, I believe.
I think is there a lab as well?
And there's probably a lab as well, yeah.
Yeah.
So it won't be there in 2.1.2?
It will not, no.
Oh, okay. Thank you.
Just a little question on mapping physical addresses
Okay.
into your address space. You show mapping it, doing your actions with it, and then unmapping it.
Yeah.
Is there anything wrong with just mapping it when you initialize the driver and leave it mapped? And what's the overhead of, or what's the benefit of mapping, unmapping every time?
Would you eventually occupy your virtual memory
Well,
table?
if your driver is going to access that memory forever, there'd be no reason for you to unmap it.
Okay.
Is there a big overhead if you're going to be unmapping it every time?
There certainly is some overhead, yeah, creating the virtual address space because the kernel keeps track of that. So yeah, there will be overhead for you mapping and unmapping it. If it's a video driver or something, or the I/O ports of a serial driver, you should just map it at the beginning of time and leave it mapped.
Okay. So as long as I'm not taking up megs of virtual address space, I can just leave it.
Right.
Okay, cool.
And there's no chance of taking up
Thank you.
so much of the translation look aside, the TLB taking up too much space with that, or is that there's no limitation on the size of those tables?
It will only matter as long as you keep accessing it. So
Okay.
if you don't access that pointer, then the TLB will get flushed with
Anyway.
other pointers.
Okay.
Yeah. In IST, after you process the data, then you call OEM interrupt done, right? And then,
No,
ISR will be
you call interrupt done.
Yep.
You call interrupt done, and then OEM interrupt done will get called later.
Okay. Yeah. And my question will be, say if I already read the data, but I need to process it, but
Okay.
I also want to allow the interrupt to come in. So can I call interrupt done before I process the data, and so it can be nested into the IST?
You can call interrupt done at any point in your IST. It really depends on your IST. Some people will actually go back to the hardware and see if there is more data available in the hardware before even bothering to re-enable the interrupt. It really depends on how your hardware is set up, which is the correct way for you to do it. If there's no processing in your ISR except to indicate to the IST, then at the bottom of your IST loop, you should probably see if there's any more data available, get that data out before you bother to call interrupt done. Because then in the same execution, you can get the next batch of data rather than waiting until you get back to the create event, or excuse me, wait for single object, which because the interrupt had already occurred would just fall through.
It's also possible that assuming you own the OAL, that at the time your ISR ran, you re-enabled the interrupt there, and the interrupt done is actually a null function. So for example, if you had a 16450 and wanted to write this virtual FIFO, you might very well have done all of the serial processing in the ISR and signaled the IST, and at that point you've already acknowledged the interrupt, and the interrupt done routine would then be null.
Okay.
Would that mean that it's possible for your interrupt service thread to be re-entered? If let's say you did have an interrupt that occurred fairly
No,
quickly.
because
Okay.
you're not going to be re-entered right waiting on an event, so all that'll happen is the event will get signaled, and you'll either process the data or go back and pick the event.
Okay.
So this virtual buffer can be shared by ISR and IST. Do you know how to do it?
There's a number of ways to do that. The easiest way is to carve out in your platform an area called driver globals, which we refer to in our sample platforms. And basically you carve out for the DNA buffers that you might need for various types of hardware. And then, for instance, your audio buffer would virtual alloc to be able to, your audio driver would do a virtual alloc, virtual copy, or mmap IO space to be able to write into that this global data, and then because it's at a fixed address in your platform, your ISR can directly point to that and use the physical addresses because it may need to set up the DMA hardware with a physical address.
Thank you.
At the keynote, they announced a common executable format. I want to know what are driver implications on this? Is Microsoft going to be supporting vendors to write drivers in this format so that I could buy a network card or whatever, PCMCIe network card, and the driver would work because the processor I happen to choose didn't support what the vendor supported.
Right. The driver with CEF, it can be converted on a desktop as well as on a device, and the end result of a conversion on the desktop is platform-specific code or processor-specific code, and that can be downloaded. It could be driver functions. It has access to all the functions that are in the OS. On device, I don't know.
The problem is it depends on what you're writing, right? So if you're writing a card and socket services driver, then yeah, all your calls are going to be abstracted, but a lot of your drivers are going to need to make specific calls to some hardware address, and I'm not sure how you would just generically pick up a driver that would work for that, of course.
I mean, if you're developing a custom board with the chip in there and everything else, well then you're going to write your own driver, of course. But if you're going to buy PC cards,
An NDIS layer or PCMCIe card, you can probably do it in that. Again, this is just coming online, so we don't have all the details, but I don't see anything that would stop you from doing that at the NS or PC card level.
Because, as an embedded developer, I mean, one of the biggest problems we have is you have a processor that you choose, you find network cards or whatever you want to use, but the drivers aren't supported. So,
there is
saying
some
this to vendors or whatever, that you have to consider the embedded people.
Absolutely. There is some loss of efficiency, obviously, doing that, and you'd have to take that into account. It depends on the driver. The other aspect is the other aspect in terms of drivers and making common drivers is what functions they call. Embedded platforms are going to have restricted subsets of the OS available. So it was brought up in the communication talk earlier that some of the Proxim driver, for instance, uses the comm control functions to put up a nice fancy configuration control panel. That makes it so that it will not run on any platform that doesn't have the GUI services that comm control needs, or comm control itself. So writing drivers, you really need to understand your target market for that driver itself. If it really is both the handheld PC devices as well as the embedded community, you might want to have a version that reduces some of the frills and has less calls into other aspects of the OS. Although in the CE driver model, you do have the flexibility to call. You can call create window, do all sorts of things, and make a driver that encompasses all the functions. It does limit the applicability to the various configurations of the OS.
I guess I'd like to see vendors maybe even create two drivers or whatever, one for the embedded world that doesn't call GUIs features, and then another driver that's great for the handhelds and everything else.
That's fine by me, and this
Piece of
audience is the
information
ones
just
writing
for
them.
other people. Thank you.
Hi, I was curious. I noticed in the serial driver code, it seems that they use mutual exclusion by using critical sections. I don't quite understand how that could be working across process boundaries. Shouldn't mutexes be used?
Any thread running the serial driver code is in the device.exe process. So even if it came from another application space, while it's actually in the device driver, it's in device.exe's process space.
Okay.
So that kind of falls into the set proc permissions, get proc permissions that he discussed. Unfortunately, it's a little more complicated than that. So if anybody wanted to know more detail, probably ask the expert tomorrow night, find me or Larry, and we can go into a little more detail and draw diagrams, because it's not that trivial.
One other comment or statement. I've been using 210 as an x86 OAL port for our specialized hardware, and now I'm starting an SH3 port, and I noticed that not even the same entry points are supported between the two NKs and the code there. For example, there's cur millisecond variable, but there's no cur diff millisecond variable. In fact, I realize now that in the SH3 platform, you actually just reach into the NK kernel, add 4 to cur diff cur millisecond counter to access cur diff. It seems kind of scary.
That was an oversight, and it has been fixed in 212.
Oh, thank you.
Thank you, though.
Hi, we have a time-critical application where we need the minimal amount of time from where we call device I/O control to when something actually happens. From what I understand, from an application, if you're calling device I/O control, device.exe will then get context switched in. We seem to be suffering a lot of overhead during that context switch. Does that make sense? Is that the way it works? I mean, when you
define a lot.
Greater than 10 milliseconds.
No, that seems excessive. So what's the priority of your application and the priority of the driver you're calling?
Oh, geez. Normal priority for the application, and I don't know, whatever the default priority for device.exe is. This is x86 running at like a DX266 kind of architecture.
The tests I've run are in the order of 100 microseconds, not milliseconds, for round trip into to device.exe, actually probably less than that.
So there's going to be a talk later where they'll actually have some examples of what the thread-to-thread switch times within a process and thread-to-thread outside of a process. And then what you're doing in this case is actually called a func or a K call, and we'll have some timings for that as well. So that number is exorbitantly large. The 10 is a little suspicious because that's the tick time. I'm wondering if you've somehow blocked and been switched out and someone else has been scheduled.
Right, that's what I was wondering.
But there's another thing in 212 now is that there's some hooks that allow you to monitor thread switches and process creations and deletions. You can actually use those to monitor the system and determine who was scheduled and why it is that they were scheduled.
Yeah, I saw that.
What session was that in? You mentioned there. Yeah.
Yeah, sorry. So the discussion, what we will have in a talk is not the thread-to-thread switching, although that might have been discussed in the applied micro demonstration. But what they will be showing is some of the timings that we can get out of the real-time benchmarks.
But they will be contrasting it to the current OS. And we have been working on that a lot for CE 3.0, so you'll see some improvements in that area for the next release, next major release.
Okay. A question related to what the original topic of this session was supposed to be, which is how the heck we debug device drivers. I guess really WinDBG, or affectionately known as WinBag, is our only option other than printf.
WinBag is one option. Another thing we frequently use is either LEDs on a platform, if you have that on your platform, or use got to get down to basics, down at the low level. We also plug in a logic analyzer into a bus and write to a bus address, much like the way the code test.
Yeah, we've done all of those actually.
So I guess the question is, are you asking for something lower than what we provide, or you just don't like WinBag?
Well, see, the ICE is really the issue. I mean, ultimately what you want is an OS-aware ICE for debugging these things.
Are you guys
want an ICE aware of the OS?
Are you guys
Yeah.
Are you guys familiar with the X-ray product?
Yeah, so the biggest problem when you start contrasting it is that we're not flat, right? So an ICE becomes much more difficult for the OEMs to implement because they have to be aware of where the DLLs have loaded and what all of our process space looks like.
Right.
So we're working on enabling them. I can't really tell you. We don't build ICE boxes. That's not our arena. So
No,
there
understood.
are people that will be supporting those.
Yeah, I guess the issue is more that, I mean, for the embedded developers that are doing device drivers, it's extremely painful right now. And I'm just looking for some help and direction as to, how to proceed. I mean, certainly logic analyzers and scopes hooked up to LEDs, yeah, we did that. It really stunk.
What was WinBag not able to do? To be honest, when we mentioned the LEDs and the logic analyzers, I do that when I'm bringing up the first 200 lines of ASM in the OAL. But all of a driver can be debugged from WinBag.
Well, the problem with WinBag is that if you've got time-critical stuff, which is time-dependent, as soon as you hit a breakpoint, you've screwed everything up. So you really, like tracing capabilities, I mean, there's a whole bunch of stuff.
Yeah, you need a hardware
The
fix.
code test demo? Code test provides non-intrusive tracing if that's what you're looking for.
Yeah, I mean, they only support pretty limited platforms right now. So.
Well, actually, I've got a... Oh, go ahead, I'm sorry.
Nothing.
Okay, no, I had a question. Is there any plans for...
This is your talk.
Well, brought up a good point. It's kind of become yours too, so... Yeah. Is there any plans for support for hardware-assisted debugging? I mean, not an ICE, but built-in capabilities for more hardware type of DDM connector as an example?
We're working with a number of vendors of these sorts of products to try and add functions in the OS. It's not all available right now, but it's things we're working on and will be available in the future.
Okay.
Yeah, I guess we just came off a 2.5-year development process where we bled profusely through the whole thing because there were lack of tools there. It's just crying for help. Thank you.
Any other questions? Oh, one more?
I had a question on when to get rid of the MDD layer, and the example that I can note is the touchscreen. I looked at the MDD layer for the touchscreen, and it implies that we're talking to an analog piece of hardware, where a lot of the touchscreen chip vendors now have a serial interface. Do you just dump the MDD layer there and kind of make it look like a mouse, or what's your suggestion on those kind of things?
Oh, you guys want to take that?
Well, yeah, you wouldn't want to make it look like a mouse, but the DDI layer that he mentioned, so basically that layer that's exported from GUI, we don't really care what you look like underneath of that, right? So you can implement whatever you want. But yeah, basically the current touch driver does assume I don't know if I'd say you're talking to analog. I mean, most of those things are delivering the data to you in a large DMA buffer.
Right.
But
Some kind of basically unfiltered data, I guess, is a better way to say
okay.
it.
Actually, I wanted to have one minor correction from the slides. When discussing the USB drivers, you mentioned that you can call load library and get proc address to talk directly to your driver. That's only applicable in device.exe space. The USB host driver is loaded in device.exe space, and your client driver, DLL, will be loaded there as well. So calling load library and get proc address in another process space would load another instance of it somewhere else, which isn't the one talking to the USB host controller. What you really need to do is your USB client driver should expose the standard stream device interface and plug itself underneath device.exe, and then you can do a create file and a device I/O control to be able to talk to that. Read file, write file, seek, whatever other APIs you want.
I'll change the slide.
As long as it's in the book. Right? It's the set of CDs you can get. It's called the Platform Builder, and that's the stuff we work on. We'll be at the Ask the Experts. You can look for any of us around. It's people with gray shirts and whatever. Grab us in the hall. We'll be glad to answer any of your questions. My name is Mark Miller. I'm the development manager for the CEOS. I'll be able to hopefully answer most of your questions or find somebody who knows the right answer.
Can I ask one more question?
Yeah.
What's the delay if you do a virtual copy into your process space and map the RAM on an ISA card or a PCI card? What's the delay between writing it in your process space and actually getting it on the card?
If it's not cached, there's no delay.
Right. So when I write to the address in my process space, I'm guaranteed that when that execution completes, it's not actually written to the card then?
If it's not cached, again, yeah. So if you do the virtual alloc and virtual alloc with the page no cache option, then it will be directly going to the hardware.
And wouldn't there be maybe a one cycle overhead for the TLB lookup, depending on the CPU? Because protected mode's active.
In terms of the cycle time of the processor, it's as the instruction is complete, it's out. Whether the fact that the TLB might have had to been reloaded underneath you is kind of invisible to your app.
We can't deal with bus delays, right? So I'm not going to promise that there's not a DMA going on and you're held off. But.
Okay. One other comment related to the last speaker. We had a lot of success using the monochrome card on the x86 platform for debugging the ISR and ISDs because it was instant and we.
Sure. Okay.
Yeah.
All right. Thank you.
Oh, I'm sorry.
That's okay. We got another line for me.
Okay.
What's the official word on how painful is it to go from a 2.0 platform driver to a 2.12? We have a project right now that we're shipping a product with 2.0. Is there compatibility, any compatibility issues?
There's a migration document that specifically addresses what you need to change, but it's honestly quite trivial. I mean, a matter of a couple days for us. I usually tell people it's not going to take them, more than a week at most for the first one, just because they usually forget to read some chapter in the migration doc.
Even with the custom OEM drivers?
Yeah, there's very little to change. I mean, we have not made significant changes between 2.0 and 2.11 and 2.12, and when 3.0 comes out, we'll again be providing a migration document. And we've tested those by actually handing them to some of our closer partners and asking them to do a port and give us feedback. So I'm pretty confident that they'll work well.
Okay, thanks.
Is it possible for third parties to implement network protocol drivers and also to create custom sockets address families?
No. You can make network protocol drivers. They just can't be exposed through WinSock. So you can make a device.exe driver, a stream driver, and make your own interface library it's a DLL that's in the application space that handles the device I/O control down to your protocol driver, but it can't be exposed through WinSock. We're investigating and are planning for a future release to be named later, the ability to have something like the WinSock version 2.0 service provider interface.
Would TDI be added as well?
Excuse me?
Would TDI be added as well?
Probably not. At the WinSock layer, you have pretty much all the flexibility you need. The TDI, the AFD interface on NT, kind of makes some assumptions in the buffering, which actually restricts the protocol driver to working in that particular mode. So you're probably better off at the WinSock layer.
Thank you.
One other question.
Okay.
There are commander device drivers. Maybe in the flash programming, sometimes you may have to disable the cache when you are programming the flash. Other times, for efficiency reasons, you may have to turn on the cache. Is there any way dynamically some of the portions of the memory could be marked as cacheable or non-cacheable?
We mentioned the virtual copy before. You can tell individual virtual addresses whether they're cached or uncached. And you can have two spaces that one is cached and one is uncached, and you can arbitrarily pick between them.
You mean create two separate things, one non-cacheable and use the non-cacheable when you are writing?
Yes.
I see. Okay. Thank you.
Keeping in mind that one of them is going to be cached, and you should make sure and flush it if you need to.
Okay, if there's no more questions, that pretty much concludes our session. Thanks for coming.